Hello everyone. Today we are going to study the details of a math coprocessor which works with the main processor and used to perform floating point operations. During the execution of a program, if the main processor finds any computations related to floating point numbers, these computations are delegated to the math coprocessor. Earlier in a topic on how 8088 works, functioning and working mechanism of 8088 microprocessor was discussed. We have seen that the processor contains large number of instructions for integer operations. The instructions required for operating on floating point numbers like addition, subtraction, multiplication and division of floating point numbers were missing in 8088 microprocessor. If the floating point computations were written by a program written in higher level language, the compiler, while generating the code, used to emulate the execution of floating point operation using the available integer operations / instructions of 8088. However, the emulator process is extremely slow and hampers the performance of applications, especially the ones using excessive floating point operations like scientific and real-time applications. So, let us start with the broad range of topics to be covered under math coprocessor. The topics are: what are math coprocessor? Second, how PC programs use a math coprocessor. That means how the programs on the personal computer make use of a math coprocessor. Which applications benefit from math coprocessor? Fourth is the potential performance gains with a math coprocessor. Fifth is how various math coprocessors work. Sixth is how a coprocessor emulator software works. So, starting with the coprocessor definition, a coprocessor in the traditional sense is a processor separate from the main CPU that extends the capability of a CPU so as to speed up floating point computations. This means that from the programs and the programmer's point of view, the CPU and coprocessor together look like a single unified machine. The 8086 CPUs, with the exception of 80486, which has a built-in floating point unit, can only handle 8, 16 or 32-bit integers as their basic data types. However, many PC-based applications require the use of not only integers but floating point numbers. A common application of floating point numbers is in scientific applications, where very small numbers in the range of 0.2 into 10 to the power minus 90 and very large numbers such as 3 into 10 to the power 10 must be accurately expressed. But floating point numbers are also useful for business applications such as computing interest in a bank or in the geometric calculations inherent in computer-aided design or computer-aided manufacturing processing. Because the instruction sets of all 80x86 CPUs directly support only integers and calculations upon integers, floating point numbers and operations on them must be programmed indirectly by using series of CPU integer instructions. This means that the computations when floating point numbers are used are far slower than normal integer calculation. Adding a coprocessor chip like 80x87 to an 80x86 based system augments the CPU architecture with 8 floating point registers, 5 additional data types and over 70 additional instructions, all designed to deal directly with floating point numbers as a basic data type. The presence of coprocessor eliminates the penalty for floating point computations and increases overall system performance for applications where excessive floating point calculations are involved. In addition to being able to quickly execute load store operations on floating point numbers, the 80x86 processors can directly perform all the basic arithmetic operations on floating point number. Besides the basic floating point operations like add, subtract, multiply and divide, Additional operations like comparisons, square roots, transcendental functions such as logarithms and sine, cosine, tangents on floating point numbers can also be performed using these coprocessors. Next, we discuss how the personal computer programs make use of 80x87 coprocessors. The basic data type used by all coprocessors is a 80-bit long floating point number. This data type requires 80 bits of storage to represent numbers which range in the size between 3.36 into 10 to the power minus 4932 and 1.19 into 10 to the power 4932. I mean, that is the range. I mean, such a large range of floating point numbers can be expressed in a 80-bit floating point numbers. For those familiar with the floating point formats, 80-bit is the floating point representation. Out of 80 bits, 64 bits are allocated for mantissa and remaining 15 bits are allocated for exponent and 1 bit is for sign bit. So, 64 plus 15 plus 1 bit makes a total of 80 bits for the floating point representation. This format provides a precision of about 19 decimal places. That means you can represent a number accurately 19 digits after decimal. The coprocessors can also handle additional data types that are converted to and from internal format upon being loaded or stored to and from the coprocessor. These include 16-bit, 32-bit and 64-bit integers as well as 18-digit BCD numbers. That means you can also have a number which is represented as a BCD number in 18 digits. That means around 9 bytes are allocated to a 18-digit BCD number. The coprocessor also supports 2 additional floating points. The short real data type, also called single precision, has 32 bits that split into 23 mantissa bits, 8 exponent bits and 1 sign bit. The IEEE single precision format provides a precision of about 6 to 7 decimal places and can represent numbers between 1.17 into 10 to the power minus 38 to 3.40 into 10 to the power 38. The long real or double precision data type has 64 bits consisting of 52 mantissa bits, 11 exponent bits and single sign bit. The long real provides around 15 to 16 decimal digits of precision and can handle numbers from 2.22 into 10 to the power minus 308 to 1.79 into 10 to the power 308. For applications like spreadsheet and databases, a coprocessor only helps if some kind of floating point computation is performed. Other than floating point computations, the performance of programs also depend on factors such as the speed of a graphics adapter in case of a computer-aided design application like CAD. Also, speed of a computer depends upon the disk performance in case of the database applications. So, the computational performance is only a fractional or small part of the total performance of the application. Most graphical user interface applications, GUI applications such as Microsoft Windows, do not get additional speed from using a mathematical coprocessor, since their graphics operations only use integer arithmetic. The window applications gain extensive GUI benefit from a graphics board with a graphics coprocessor that speeds up certain common graphics operations such as line drawing or picture rotation. Note that the coprocessor performance also depends upon the motherboard or more specifically the chipset used on the motherboard. In absence of a coprocessor, the floating point calculations are often performed by a software package that simulates floating point operations. Let us say we wish to add 2 floating point numbers as given below. One number is 0.1234 into 10 to the power 4 and another number is 0.3423 into 10 to the power 6. In order to add these two floating point numbers, the number can be represented as an integer pair 1234, 4 and 3423, 6. Both mantissa and exponents are represented as integer. The first step of floating point addition is the exponents are compared for equality. In the second step, in order to make the exponents equal, appropriate shift in the mantissa equal to the difference between exponents of the mantissa of the number having smaller exponent takes place in the second step. The third step is the addition of mantissa. In the current example, the 0.1234 will be shifted by 2 digits so as to become 0.001234. It will then be added with 0.3423 to result in 0.3435, and therefore the final result is again a pair of integers. This way we have seen how a floating point addition is simulated or emulated with the help of integer operations only. In the earlier days, the floating point arithmetic was simulated with the help of integer instructions available in the processor, whereas the coprocessor directly performs the floating point addition in the hardware, resulting in manifold performance improvement over simulation using integer operations. A program designed to handle different floating point operations is called a coprocessor emulator. Simulating the coprocessor has the advantage for application programs that identical code can be generated for use with either the coprocessor and the emulator, so that it is possible to write programs that run on any system without regard to whether a coprocessor is present or not. Whether the program will use an actual processor or software emulating it can easily be determined at runtime by detecting the presence or absence of a coprocessor chips. Two approaches to interface an 8087 emulator to programs are common. The first method makes use of the fact that all coprocessor instructions start with the same 5-bit pattern 11011. Thus, the first byte of the coprocessor instruction will be in the range D8 to DF as per the first 5 bits we have seen earlier, D8 to DF hexadecimal. In addition, the coprocessor instructions usually are preceded by a wait instruction. The opcode of the wait instruction is 9B hex, which is 1 byte long. The second method to interface an emulator is only available on 286, 386 and 486 machines. If the emulation bit in the machine status word of this processor is set, the processor will generate a software interrupt 7 through the INT07 instruction. Whenever a coprocessor instruction is encountered, the vector for this interrupt, which is 07 into 4 equal to 28, that means 28th memory location onwards will be set in a manner so as to point to the emulator package that decodes the instruction and performs the desired operation which was supposed to be done in the coprocessor hardware. This approach has the advantage that the emulator can reside as a device driver in the memory and share a common code across multiple programs needing emulator. This implies that the emulator code need not be included in the program code, but can be loaded once as a terminate and stay residence program TSR or a device driver program and then used by every program that requires a coprocessor. The emulation via interrupt 7 is transparent, which means that the programs containing coprocessor instructions execute just like a coprocessor was present. The only difference will be that the emulator is slower. Even programs that require a coprocessor to run like AutoCAD are fooled to believe that a coprocessor is present with emulators using INT7 instructions. The earlier versions of the operating system such as Windows 3.1 provided coprocessor emulations using INT7 instructions automatically if the operating system do not find a coprocessor to be installed. The emulator in Windows is very slow as instead of executing the instructions in hardware directly in coprocessor, the emulator executes these hardware instructions into a set of equivalent software instructions in the available processor. So, what we have learned today are the details of math coprocessor used exclusively for floating point calculations. Earlier in a topic on how 8088 works, functioning and working mechanism of 8088 microprocessor was discussed. We have seen that the processor contains large number of instructions for integer operations. The instructions required for operating on floating point numbers like addition, subtraction, multiplication and division of floating point numbers were missing in 8088 microprocessor. The compiler used to emulate the execution of floating point operations using the available integer operations of 8088. However, the emulator process is extremely slow and hampers the performance of the applications, especially the ones using excessive floating point operations like scientific and real-time applications. Earlier, due to limitations in the VLSI technology, the coprocessor was designed as separate chip in combination with the main processor performing the integer operations till the evolution of 80486 processor, which required the support of 80487 for floating point operations. The main processor and coprocessor were separate chips installed on the motherboard in such a manner that they behaved like a single processor with extended functionality of floating point operations. However, with the advancement in the VLSI technology, all the processors designed after 80486, say Pentium series since last 15 to 20 years and Itanium series, which is the latest one, had coprocessor also fabricated inside the main processor so as to support floating point operations. The compiler generates the code in a manner that it exploits the available hardware for speeding up the floating point operations. In short, the coprocessor these days is bundled in the main processor to support the extended floating point operations. Thank you.